Hello and good afternoon, everybody. Welcome to the first of SKC's Summer 2021 WebIH series. Just to start out with some housekeeping, all attendees will be on mute automatically. If anybody has questions, either during or after the presentation, please enter your question into the chat or question panel to be answered at the end of the presentation. My name is Dan Baldoff, Business Innovation Manager at SKC. Today's session is titled ISO 17025 versus NIST-traceable calibration, which is right for me. This is a question that customers and colleagues frequently ask me, and I learned a lot while preparing for the session, so I hope that it is informative and valuable to you. Now, just to start off a little bit about me, you can't see me on video, so I threw a photo up here. I've been part of the SKC team since June 2010. I first served as a summer intern in SKC's product development department for 2 years and graduated in 2012 with my BS in electrical engineering. Then served 6 years as an electrical engineer, and the team that I was a part of was responsible for the development of the AirCheck Touch, the Pocket Pump Touch, and I also participated in part of the development of AirCheck Essential and Connect pumps. Spent the last 3 years in my current role as Business Innovation Manager, during which time I completed my MBA with a concentration in business analytics. Today, I devote my time at SKC to solving problems that drive business value. And that's enough about me. You came here to learn about calibration, so on to that. I'm going to cover 3 topics today, followed by a Q&A. First is an overview of what it takes to be accredited to ISO IEC 17025-2017. Second is the calibration service offerings of SKC's Cal Lab and the differences between our NIST and ISO accredited procedures. Then third is some advice on which level of service offering is right for you. When preparing for this, I thought, who better to explain what ISO 17025 is than ISO themselves? So here we have 2 direct quotes. They state, ISO IEC 17025-2017 specifies the general requirements for the competence, impartiality, and consistent operation of laboratories, and also that the standard enables laboratories to demonstrate that they operate competently and generate valid results, thereby promoting confidence in their work, both nationally and around the world. So what are the primary requirements for being accredited to 17025? This list here is not exhaustive. I will step through each one of these, but this is sort of an overview of the high points, like what I feel to be most important in complying with 17025. So number 1 is impartiality. ISO defines impartiality as the presence of objectivity. ISO requires that all laboratory activities are undertaken impartially and structured and managed so as to safeguard impartiality. And each accredited laboratory must be able to demonstrate that they continually assess risks to impartiality and have installed structural safeguards and/or have taken mitigating actions against those risks. So this is one of the most, if not the most important parts of ISO 17025. Next is confidentiality. Each laboratory is contractually responsible for the management of information gathered during the performance of lab activities. The standard requires labs to inform customers in writing if any information is to be made publicly available, which isn't like a typical thing. We have confidentiality policies that would stop us from releasing things to the public, but that's in the standard. All personnel shall keep all information obtained during the performance of lab activities confidential, except as required by law. And in this case, that would be like if SKC were subpoenaed and a court of law wanted to review calibration certificates or something like that. So SKC's calibration laboratory treats all customer information as confidential and has procedures to safeguard against any release. ISO 17025 also requires that organizations have a defined quality management system. SKC's QMS is assessed by SAI Global to comply with ISO 9001:2015. SKC also maintains a supplemental quality manual for the calibration lab that has some very specific ISO 17025 requirements in it. All procedures of the calibration laboratory and all other activities at SKC are documented. That's part of this requirement. Next, ISO requires that laboratories have competent personnel. Personnel must have the authority and resources needed to carry out their duties. Each employee in our lab is trained and qualified to perform the documented activities needed to complete their function. And each employee is also trained to identify when changes are needed, request an update to procedures or documentation as part of continuous improvement. To be accredited, you need to have an accreditation body who regularly audits the organization. So we work with Perry Johnson Laboratory Accreditation, or PJLA, and they conduct audits of the laboratory's quality management system annually in order to assess our competency. We also have internal audits. SKC has a team of trained internal auditors for 17025 who walk through a similar audit process to our accreditation body. These audits are documented and available upon request to our accreditation body. All standards used in testing must be traceable. So when we send our standards out, they're sent to a trusted ISO 17025 accredited calibration laboratory. We receive a calibration with stated uncertainties, which I'll talk about a little later. The standards that the calibration lab we send our standards to must be traceable to the International System of Units through NIST. And then when we receive the standards back, each certificate is reviewed, the device is tested, and the laboratory technical staff determines if any changes need to be made to our measurement uncertainty budgets or any other operating procedures or policies within the lab. We also do interlaboratory comparison. The laboratory conducts this, it's called ILC, annually as part of its measurement assurance plan. A unit is calibrated first at SKC with stated uncertainties. It's then sent to a vendor for an accredited calibration, returned to SKC and calibrated again. And we calculate a normalized error between the laboratory results, and determination is made if the results are satisfactory or unsatisfactory. Obviously, there need to be some type of corrective action put into place if you had unsatisfactory results. But this is a regular activity that we do just to ensure that there is no drift in our standards, and that we are proficient enough to complete these activities. The laboratory continually logs temperature, atmospheric pressure, and humidity in all rooms used for calibration activities. We control our temperature and humidity within 20 degrees Celsius plus minus 2 degrees and 50% relative humidity plus minus 20%. Changes in environmental conditions during an accredited calibration are logged and actually affect the measurement uncertainty budget. They're continually monitored during accredited calibrations. Next, we'll talk about measurement assurance. The laboratory conducts regular artifact testing on our standards to determine if there's any unacceptable drift that's occurred between our standards calibration interval. If this artifact testing produces any anomalous results, all equipment is then quarantined from being used in customer calibrations until a root cause analysis is completed. And then finally, and this I think is really one of the most powerful things about an ISO accredited calibration is the idea of generating a measurement uncertainty budget. SKC, when we do a calibration for volumetric flow rate, we take into account 6 different sources of uncertainty. There's the rated accuracy of the standard that we have from the manufacturer. There is the reported uncertainty of the standard that comes from the calibration certificate. There's the resolution, so how many digits can the device display if it has a digital readout. Repeatability of the sampled test points. So we actually take the sampled test points and plug them into our measurement uncertainty budget, and that will affect it if there is variation during the test. Any temperature deviation during the test, and any atmospheric pressure deviation. Like I said, these sources are collected on a budget, they're evaluated statistically, and then a final number is reported on the calibration certificate, and we call that the expanded uncertainty. That is all of those sources rolled up together to give you an expanded uncertainty. So talking about measurement uncertainty, it's a little bit of an abstract topic, and I put together this example here to hopefully help you to understand better why you want to calculate measurement uncertainty. This is extremely simplified, just to say this only takes into account the source of measurement uncertainty for the resolution of the device. Typically, you would have multiple items rolled up in here, but for the sake of this example, I felt like it was much simpler this way. So let's say you have a metric roller that has markings in centimeters and millimeters, and you need to measure a block. So you determine the length is between 7.5 and 7.6 centimeters. If you zoom in there real close, you can see that's where it's showing up. So the measurement uncertainty in this case is half of the smallest marking or gradient on the measurement device, or 0.05 centimeters. So that's half a millimeter. And the length of the block would be represented as 7.55 centimeters plus minus 0.05 centimeters. So to expand on that a bit, let's assume that you have a metric roller with markings only in centimeters, and you're measuring the same block, but this time you can only determine that the length is between 7 centimeters and 8 centimeters. The measurement uncertainty in this case is half of the smallest gradient of the measurement device, or half a centimeter, and the length of the block would be represented as 7.5 centimeters plus minus half a centimeter. Now, why does measurement uncertainty matter? Let's take the results of the last 2 examples and plot them here on a control chart. The top and the bottom red lines there represent a process requirement. So let's say we use this block in a production process or somewhere where, in order for it to work properly, the length of it must be between 7.3 and 7.7 centimeters, which is once again marked in red there. Both of the results fall within that range, but if you see, the uncertainty varies significantly due to the different devices or methods used to measure these blocks. We would say that measurement 1 conforms, but measurement 2 is indeterminate. The actual result of this measurement could be up at 7.9, it could be down at 7.1. We cannot tell with the device that we used. So now that I've gone over that, let's talk through SKC's calibration services offering. Our scope of accreditation, this is on our certificate of accreditation, which can be found on Perry Johnson Laboratory Accreditation's website. But SKC's lab is accredited for measuring gas flow rate in the ranges of 10 to 500 milliliters a minute, so for low flow devices, and from 500 to 10,000 milliliters per minute. And our calibration and measurement capability, which is essentially the best uncertainty attainable in ideal conditions is at this point 0.27% of reading. So we have two types of devices here, and you can see them referenced up in the upper right corner there. We have a piston prover and a clearance sealed piston prover. The piston prover is a mercury sealed device, and it has the range of 500 to 10,000 milliliters a minute. And we use this device for calibration using a pressurized air source. We also have a clearance sealed piston prover with multiple flow cells that allow a range between 10 and 50,000 milliliters per minute. This can be used for calibration using vacuum or pressure air source. So what is our service offering? SKC services and calibrates two primary types of instruments. We have our SKC checkmate units in low, medium, and high flow. We also do MESA or BIOS Defender and DC light units. SKC only offers ISO accredited calibrations on the low and medium flow devices right now, but we're looking to add the high flow to the scope of our accreditation by the end of this year. What do we do when we receive your device? We disinfect it first and foremost in the time of COVID especially. We functionally inspect your unit, and we allow it to acclimate in the controlled environment of the laboratory for 24 hours before any service occurs. If there's any problem found at this point that requires repair, like if your device doesn't power on, if the battery is dead, we will then contact you and request that you give us authorization to repair. And if we're unable to repair the device, we likely will either return it to you or send it to a third party. So now we'll get to the meat of it here. For our NIST calibration, this is a little bit of a simplified version of what happens during the NIST calibration procedure, but I'll walk through this. The unit under test is connected to your airflow source and your standard. Using a precision needle valve, the technician sets the flow to approximate the flow set point. You record temperature, atmospheric pressure, and humidity at the beginning of the test, and then you take three measurements. First, or a series of three measurements. First, there are 3 points from your standard device, and that's before. Then you take 10 points from the unit under test, followed by 3 more points from the standard. So the average of the before and after measurements on your standard is calculated. The average of the unit under test readings is calculated, and then you calculate a deviation. You repeat this test for all 5 specified flow set points, and if the unit is within specification, the technician will prepare a certificate. If it's out of spec, checkmate units will be adjusted and the procedure will be repeated again. You'll get both sets of data, both as found and as shipped. If the unit is out of specification and SKC is unable to adjust the unit, you'll receive a test report outlining the issue. And just as a housekeeping thing here, the technician and another independent team member review each calibration certificate content for accuracy. They're just basically ensuring that there are no typos, that everything has been entered properly. And here's what one of our calibration certificates looks like. It's relatively simple. This is for NIST-traceable calibration. For ISO accredited calibration, it's a similar process, but I'll detail some of the differences here. The unit under test is connected to the airflow source in the standard. Technician using the precision needle valve sets the flow rate. Your temperature, atmospheric pressure, and humidity are recorded. And before taking any measurements, the technician notes the time. So your series of measurements are then recorded for each flow set point. And after your measurement is completed, the time is noted again. The average of your before and after standard measurements is calculated. The average of the unit under test readings is calculated. And your tests are repeated for all specified flow set points. Technician calculates a deviation. Then they download data from our environmental monitor. This is 10-second intervals throughout the calibration routine. And they determine the absolute variation in temperature and pressure during each measurement time period. And then the technician will generate a measurement uncertainty budget for each flow point. So there are typically 5 measurement uncertainty budgets that go along with each certificate. So this budget takes into account, once again, accuracy, uncertainty, repeatability, resolution, temperature, and pressure. And you can see here, each of the uncertainties add up. You get a combined standard uncertainty. We multiply it by a coverage factor, K equals 2, and you get a number which is called the expanded uncertainty. That's what's reported on your calibration certificate. The technician evaluates whether the device is in specification. If it's within tolerance, a certificate with only the as-shipped data will be generated. If it's out of tolerance and can be adjusted, the technician will service the unit and then repeat the complete procedure, including the estimate of measurement uncertainty for all of the 5 new flow points. And if the device cannot be adjusted, an as-found test report will be issued, and the customer will need to determine a disposition for it. Then finally, before the certificate is issued and the device is shipped back to you, a technically competent team member independently reviews all worksheets, certificates, measurement uncertainty budgets, and any other supporting documentation to ensure that the calibration results are valid as reported. So there's a more thorough review process that happens here. And here's a view of one of our accredited certificates. So to give you a real quick comparison, ISO and NIST both use NIST-traceable standards. They both have testing that's completed using documented procedures. Testing is completed in controlled environments with both service offerings. Your initial environmental conditions are reported, but for ISO, you do have that continual monitoring throughout the test. You have the measurement uncertainty estimated and reported for each flow point. You have an independent review of all reported results by a technically competent third party, and you have the internationally recognized accredited calibration certificate. So I'll try to, move through these relatively quickly because I'm running a little late, but let's talk about which service level offering is right for you. So the pros of NIST: you have traceable results reported by SKC. Your testing is conducted in controlled conditions, and it's a cost-effective method of compliance. Pros of ISO: your traceability is verified by a third party. It's an internationally recognized calibration. There's this additional review of both the measurement results and all of the worksheets that are used to generate them. Your environmental conditions are continually monitored during the calibration. You have the repeatability study of the measurement points, and your measurement uncertainty is calculated with each flow point. So who chooses ISO calibrations? You could have an organization looking to calibrate an end-use device like a field rotometer, or a laboratory that uses a device under test as a standard. There are firms that have quality management system requirements that require an ISO cal on all equipment. You may be a business that operates internationally that wants to standardize your calibration requirements. You could private and governmental organizations who conduct activities in which the risk of non-compliance would lead to a significant liability, or organizations just looking for additional assurance in the results on the certificate. So how to choose? You determine what accuracy is required per your sampling method, and conduct a risk assessment to determine how critical the calibrator is to the accuracy of your overall results. And another step to take is to contact your quality department and ask specifically which service level they prefer or require. that is all that I have here. Thank you to Denny Collins, who is on the call here and will help me answer questions. David Erickson, our CalLab tech, who does this work every day. Matt Bonadillo, our electronics engineer, who started the calibration lab and has served as like a technical liaison throughout all of this. And Michelle Philby, our marketing facilitator, who set this up. And also to everybody else tuning in. If anybody has questions, I believe that Denny will read them off here and we will attempt to answer them. If we run out of time, we will get back to anybody whose question is missed.
Okay, first question, and again, Dan, thanks. It was a very informative presentation. The first question is a pretty simple one. Can we get a slide deck? There's some good information about pros and cons. Yeah, there will be a slide made available here shortly. We'll get that out to the attendees. The other question, Dan, that came in was, is there a difference in measurement uncertainty and instrument accuracy?
Yeah, and I can go back here and sort of recap that. Let me run back to this slide on measurement uncertainty. So this is like a very simplified example here. And, essentially with a roller, you don't have a whole lot of sources of uncertainty. So in like a real life example, if you had a calibrator in here, generally the positive and negative error bars for just the accuracy of the device would be significantly less than the expanded uncertainty of the device, because we do take into account all of these sources of uncertainty, the accuracy of the device, the uncertainty from the calibration certificate from the manufacturer of it or the lab that calibrates it, the repeatability of the points tested, resolution, temperature, and pressure. So it's to answer in a more succinct way, measurement uncertainty includes the accuracy of the device and expands upon it.
Okay, one other question here, I think, Dan, or maybe it's a comment. The 5 measurement series you were talking about for NIST and ISO traceability calibration were not clear. Is there, can you go back to that and maybe clear that up just a little bit?
You want me to go to NIST?
Yeah, I'm not sure of the question, if it was a statement.
Yeah, we take 5 points, and for certain devices, it's 1 liter, 2 liter, 3 liter, 4 liter, 5 liter. For others, we go lower to like 500 milliliters a minute, 1 liter, 2 liter, 4 liter, 5 liter. But it varies based on the device. That's why I left it vague. I hope that answers the question.
Okay, that's all we had as far as comments and questions go. Again, we thank everyone for attending this WebIH webinar, and stay tuned for more coming later this summer. Hope everyone has a great day. Thanks again, Dan, did a great job.
Yeah, thank you, everybody.